Now, additional exercise, example 1.25. An oil drop of 12 excess electrons is held stationary under a constant electric field of 2.55 into 10 raised to 4 Newton per Coulomb in Millikan's oil drop experiment. The density of the oil is 1.26 gram per centimeter cube. Estimate the radius of the drop G, that is 9.81 meter per second square, E, that is equal to 1.6 into 10 raised to minus 19 Coulomb. Now see, number of excess electrons n equal to 12 given to you. Electric field, that is 2.55 into 10 raised to 4 Newton per Coulomb, that is also given to you. Then after, density, that is 1.26 gram per centimeter cube. So that will be equal to 1.26 into 10 raised to 3 kilogram per meter cube. G, that is 9.81 meter per second square. E, that we have to take 1.6 into 10 raised to minus 19 Coulomb. Now, when the oil drop is with some amount of charge Q and it is placed in the electric field E, then the force on it, that is Q into E. And when it is in the air, the gravitational force in downward direction, that is mg. So here two forces will act on the drop. Now if you want to hold it stationary, then these two forces should be equal in magnitude and opposite in direction. Weight mg, that is always vertically downward. It implies that the force due to electric field, that should be in upward direction, and magnitude wise mg and qe both should be equal. Now mass of the drop, that is volume into density. Volume of the drop, that is 4/3 pi r cube into density G as it is. Now Q, amount of charge on the drop. So n excess electrons are there, and per electron the charge is E. So total charge, that is Ne into capital E. So R cube, that is equal to 3NEE upon 4 pi rho G. So R, the radius of the drop, that is 3NEE upon 4 pi rho G whole raised to 1/3. Now in this equation substitute N equal to 12, E 1.6 into 10 raised to minus 19, E 2.55 into 10 raised to 4 upon 4 into 3.14, density, that is 1.26 into 10 raised to 3, G 9.81. Then solve it, and then after take a cube root of it, you will get radius of the drop. Clear? Now 1.26. Which among the curves shown in figure cannot possibly represent electrostatic field lines? Now see figure A. So we already studied about the electrostatics of conductors. In that we discussed this thing, electric field at each and every point on the surface of the conductor, that is normal to the surface. So first one is wrong one, then second one. So we know this thing, electric field lines never come out from the negative charge. Here it is represented come out from the negative charge. So second one is also wrong one, means figure B is wrong one. C is right, correct one, because from positive charge the field lines comes out and extends up to infinity. Then figure D, okay, two field lines never intersect each other, and therefore figure D, that is also wrong one. And E, field lines, electric field lines never form a closed loop. So E, that is also wrong one. Here we have to represent which among the curves cannot possibly represent electrostatic field lines. So we can write the answer A, B, D and E. Clear? Now 1.27. In a certain region of space, electric field is along the z direction throughout. The magnitude of electric field is, however, not constant but increases uniformly along the positive z direction at the rate of 10⁵ Newton per Coulomb per meter. What are the force and torque experienced by the system having a total dipole moment equal to 10⁻⁻7 Coulomb meter in the negative z direction? So see the figure. This one is the z direction. Electric field is in z direction. And now the dipole is along the z direction, plus q minus q. So dipole moment, that is in negative z direction from minus q to plus q. Suppose the separation between these two charges that we consider is z meter. That is z meter. Okay. So the dipole moment, which one is given to you here? So we can write dipole moment P, that is q into z, that is the distance between these two charges, and that is given to you 10⁻⁻7 Coulomb meter. Now we want to calculate force and torque. So first of all, we have to think about the force acting on positive charge due to this electric field, then force on negative charge due to this electric field, and then after we have to take resultant. So we know this thing, when any charge q is placed in electric field E, the force acts on it, that is q into E. So force on positive charge plus q, that is q into E. Okay. Then force on negative charge. So first of all, if we consider the electric field at the position of plus q, that is E, then we have to first consider the electric field at the position of minus q. Now here it is given to you per meter 10⁵ Newton per Coulomb field increases. So if per meter 10⁵ increase, then per z meter how much increase is there? Because distance between plus q and minus q, that is z. So electric field at the position of minus q, that we can write E at the position of plus q, then in distance z, the increase, that is z into 10⁵. So total is E plus z into 10⁵. Now force on minus q, that is equal to q into E plus z into 10⁵. Now force on plus q, that will be in the direction of electric field. Force on minus q, that will be in the opposite direction of electric field. So net force, that is F equal to QE plus QZ into 10⁵, that is the force on minus q, and that is in opposite direction of electric field, and on plus q in the direction of electric field, but the force on minus q, that is greater than the force on plus q. So force on minus q charge minus force on plus q charge. So QE cancelled. You will get QZ into 10⁵, but QZ, that is 10 raised to minus 7. That is the dipole moment given to you. So substitute. So resultantly, you will get the force on the dipole in negative z direction, that is 10 raised to minus 2 Newton. Now, the angle between dipole moment and electric field, that is pi, 180 degree. So, torque acting on the dipole, that is Pe sine theta. Theta is 180, sine 180, 0. So, torque acting on the dipole is 0. Clear to all of you? 1.28. A conductor A with a cavity as shown in figure A is given a charge capital Q. Show that the entire charge must appear on the outer surface of the conductor. B. Another conductor B with charge Q is inserted into the cavity, keeping B insulated from A. Show that the total charge on the outside surface of A is capital Q plus small q. Figure B. See, a sensitive instrument is to be shielded from the strong electrostatic field in its environment. Suggest a possible way. Now see here, suppose we place charge capital Q on the conductor A. So we already studied about the electrostatics of conductor. Inside the conductor, electric field is always 0. So here if we consider a Gaussian surface very close to this outer surface of the conductor here, but inside the conductor. So very close to this surface here inside the conductor, if we consider the Gaussian surface, and then if we apply the Gauss's theorem, then we can write integration E dot ds, that is Q upon epsilon 0 as per this. Q, the net charge enclosed by this Gaussian surface, that is 0. So here we can write equal to 0. So when net charge enclosed by this Gaussian surface is 0, means entire charge Q is outside the surface. So we can say that entire charge placed on the conductor, that will be distributed on the surface of the conductor. Now second, when in this particular cavity another conductor with charge small q is placed, which is insulated with respect to A. So here if small q charge is placed in the cavity, then at the surface of the cavity minus q charge will be attracted by it. So that minus q charge will be distributed at the surface of the cavity in the conductor. So if minus q amount of charge is accumulated here at the surface of the cavity, then at the surface of the conductor plus q charge will be free. So in that case, the net charge on the surface of conductor A will be capital Q plus small q. Now, third question. We know this thing. If any type of external field is there, but for the conductor with cavity, inside the cavity, the electric field is always 0. So, if you want to shield the sensitive instrument from the strong electrostatic field, then you have to place it in metallic case. So metallic case form a cavity, simple thing. Clear to all of you? Now 1.29. A hollow charge conductor has a tiny hole cut into its surface so that the electric field in the hole is sigma upon 2 epsilon 0 n caret, where n caret is the unit vector in the outward normal direction and sigma is the surface charge density near the hole. Now see here, this figure. This one is the hollow charged conductor. Okay, and this one is the tiny hole cut into the surface. Now, suppose first we think about the electric field at point A, which one is at the surface, the electric field, and at point B, which is just inside the surface in this hole of the charged conductor. So electric field E1, that is at point A and at point B, that is due to the entire cell except this particular material of the cavity which originally was there. એટલે અહીંયા જ્યારે આ મટીરિયલ હતું ત્યારે આ કેવિટી ના કહેવાય, પણ હવે આ મટીરિયલ અહીંથી આપણે કાઢી લીધું એ પછી A અને B પાસેનું ફિલ્ડ આપણે E1 લીધું. ઓકે, હવે A અને B પાસેનું ફિલ્ડ આ કેવિટી ના બનાવી હોય, મતલબ કે if entire conductor is solid one, in that case electric field at A and B. Okay, तो A केस में electric field because of the material which were there originally in the place of cavity. Okay, now if entire conductor is without cavity, means it is perfectly solid one. So in that case the electric field at point A, that will be sigma upon epsilon 0, that we studied in theory. And if we think about the resultant electric field, that is E1 plus E2, then it will be also sigma upon epsilon 0. B point, that is inside the conductor, and inside the solid conductor the electric field is always 0. It implies that if we think about E1 minus E2 here at B, net field, that is 0. So E1, that is equal to E2. Now if we consider E1 that is equal to E2, then here if we substitute the value of E1, that is equal to E2, so 2E1, then E1 equal to sigma upon 2 epsilon 0, and electric field that is always radially outward. So as per question, we proved it, it is sigma upon 2 epsilon 0 n caret. Clear to all of you? Example 1.30. Obtain the formula for the electric field due to a long thin wire of uniform linear charge density lambda without using Gauss's law. Using Gauss's law, આપણે આ equation already derive કરેલું છે અને એકદમ સિમ્પલેસ્ટ વેમાં આપણને ઇક્વેશન મળી ગયું હતું. આ પ્રોબ્લેમ સોલ્વ કરીશું એટલે આપણને ગોસીસ લો નું ઇમ્પોર્ટન્સ ખ્યાલ આવશે કે કેટલું ઈઝી પડે આપણને. Gauss's law is very useful to find the electric field at any point due to symmetric charge distribution. હવે જો અત્યારે આપણે without using Gauss's law electric field find out kariye. Now see, this one is uniform linear charged wire, okay, having linear charge density lambda. Now suppose we want to find the electric field at point P, which one is at perpendicular distance r from the wire. Okay, now here we consider the origin x equal to 0 here. With respect to that On y-axis we take point P, which one is at distance r. Okay, wire is coinciding with x-axis. Now here we have to divide this entire wire into so many infinitesimal small line elements. Then due to each line element, which one is charged one, we have to find the electric field at point P. And then after, we have to take vector summation of all those fields to calculate the resultant electric field. This one is the concept. Now see, first we consider here infinitesimal small line element having length equal to dx, on which charge residing, that is dq. And with respect to this particular element, suppose point P is at a distance a and this element is at a distance x from the origin. Then electric field due to charge dq, which we can consider now point like charge, because this element is infinitesimal small. So dE, that is k dq upon a square. So 1 upon 4 pi epsilon 0 into dq. Now charge per unit length is lambda. Therefore, charge on length dx is how much? So lambda into dx. So dq, that is lambda into dx. Then a. So we can use Pythagoras theorem. A square, that is r square plus x square. So this is the electric field at point P due to charge dq. This charge dq is positive. It implies that at point P the electric field will be outward. So direction of the electric field dE, that will be as shown in the figure. Here this angle is considered theta. So this angle will be also theta. So we can take two components of the electric field dE. One that is in y direction, dE cos theta, because this angle is theta. And another one in this x direction, specifically it will be in negative x direction, that is dE sin theta. But see here, we can consider another infinitesimal small element, which one is at a distance minus x from the origin, with same length equal to dx. So charge on it, that will be also dq. And due to that electric field, that will be in the direction which one is represented here by black arrow. Now if we take two components for this electric field, then one dE cos theta will be in y direction, in the direction of this particular component of the first electric field. Then dE sin theta will be opposite to this first dE sin theta component. It implies that dE sin theta components will be cancelled. dE cos theta, these components perpendicular to the wire in y direction will sustain. But the components which are parallel to the wire, dE sin theta, will be cancelled. It implies that now we can say the contribution in the electric field of this particular element, that will be only dE cos theta, because dE sin theta will be cancelled by similar other element. So we can write now dE dash, this one is the electric field due to this small element having length dx with charge dq, that is dE cos theta at point P. So dE dash, that is, now substitute the value of dE, that is 1 upon 4 pi epsilon 0 lambda dx upon r square plus x square cos theta, that is adjacent upon hypotenuse. So that is r upon under root r square plus x square. Resultantly, we will get 1 upon 4 pi epsilon 0 lambda r dx upon r square plus x square raised to 3 by 2. These two jointly will give you raised to 3 by 2. Now to find out the resultant electric field at P, we have to consider this type of so many infinitesimal small elements starting from x equal to 0 to x equal to infinity, as well as on left hand side starting from x equal to 0 to x equal to minus infinite. And then after we have to take the summation of all those. It implies that we have to integrate this equation between the limits minus infinity to plus infinity. But for that integration, we have to change the variables. Okay. Now see, in figure we can observe this thing tan theta, that is x by r, opposite upon adjacent. So x equal to r tan theta. So we can write dx, that is r sec square theta d theta, differentiation of this one. Now r square plus x square, that we can write r square, substitute the value of this x. So x square, that is r square tan square theta. So resultantly we can write that is r square into 1 plus tan square theta. But 1 plus tan square theta, that is sec square theta. So r square plus x square, that is r square sec square theta. So r square plus x square raised to 3 by 2, that is r square sec square theta raised to 3 by 2, that is r cube sec cube theta. It implies that here x is changed in theta because integration from minus infinity to plus infinity, that will be somewhat complex one. Now see our equation, that is dE dash equal to 1 upon 4 pi epsilon 0 lambda r dx upon r square plus x square raised to 3 by 2. હવે આ બધી જ વેલ્યુઝ આપણે જે ચેન્જ કરીએ આમાં સબસ્ટિટ્યુટ કરીએ. dE dash equal to 1 upon 4 pi epsilon 0 lambda as it is, r as it is, dx. So see, this is the value of dx, r sec square theta d theta. So r sec square theta d theta upon r square plus x square raised to 3 by 2. See, this r square plus x square raised to 3 by 2, that comes to r cube sec cube theta. So r cube sec cube theta. So here this r square. So r square cancelled. So 1 r will be there. Sec square theta sec cube theta. So in denominator sec theta will be there. Resultantly we will get dE dash equal to 1 upon 4 pi epsilon 0 lambda by r cos theta d theta. Now, if the variable is changed, limit will be changed. Now see here. If x tends to infinity, suppose we take x somewhere here, element distance somewhere here, then we have to join the line like this. So this particular angle theta will increase. So if this particular end of the wire is extended up to infinity, then here this particular line joining to P and the element at infinity, that will be almost parallel to the wire. And if it is almost parallel to the wire, then this theta tends to pi by 2. On this side, we can write theta tends to minus pi by 2. It implies that now, if x tends to plus infinity, theta tends to plus pi by 2. X tends to minus infinity, theta tends to minus pi by 2. So, integration of this equation, now that we have to carry out between minus pi by 2 to plus pi by 2. So, resultant electric field E, that is integration minus pi by 2 to plus pi by 2 dE dash. But in that, lambda upon 4 pi epsilon 0 r, that is constant, so take it outside the integration. Integration minus pi by 2 to plus pi by 2 cos theta d theta. Lambda upon 4 pi epsilon 0 as it is. Integration of cos theta, that is sin theta, limits minus pi by 2 to plus pi by 2. Lambda upon 4 pi epsilon 0 as it is. First theta equal to upper limit, so sin pi by 2, then minus theta equal to lower limit, so sin minus pi by 2. Sin minus pi by 2, that is minus 1, so minus minus plus. Resultantly, we will get lambda upon 4 pi epsilon 0, 1 plus 1. So, resultant electric field E, that is lambda upon 2 pi epsilon 0 r. In vector form, we can write vector E, that is lambda upon 2 pi epsilon 0 r, r caret, where r caret is the unit vector in the direction of electric field. So lengthy calculations, but by using Gauss's law, simply we can calculate this electric field. Clear to all of you? Now 1.31. It is now believed that protons and neutrons, which constitute nuclei of ordinary matter, are themselves built out of more elementary units called quarks. A proton and a neutron consist of 3 quarks each. 2 types of quarks, the so-called up quark denoted by U of charge plus 2 by 3e, and the down quark denoted by D of charge minus 1/3 e, together with electrons build up ordinary matter. Quarks of other types have also been found, which give rise to different unusual varieties of matter. Suggest a possible quark composition of a proton and neutron. In short, we have to think about 2 quarks up and down, and their charges are plus 2/3 e and minus 1/3 e respectively. Then we have to think about the possible composition of proton and neutron. Now charge of proton, that is plus e, charge of neutron, that is 0. So we have to take 3 quarks and we have to take a combination of these 2 types of quarks in such a way that the resultant charge on the proton, that should be E, and resultant charge on the neutron, that should be 0. Now see, for up quark plus 2/3 e, for down minus 1/3 e. So for proton, the possible combination, that will be up, up, down. For up, charge is 2/3 e. For up, 2/3 e. Then for down, minus 1/3 e. If we take the summation of all these charges for this particular combination, then we will get resultant, that is E. Then for neutron, we can suggest U, D, D means up, down, down. If we take the summation of these 3 charges, plus 2 by 3 e minus 1/3 e minus 1/3 e, then resultant will be 0. Clear? So these are the possible composition of proton and neutron. Clear in terms of quarks. Clear? 1.32. A. Consider an arbitrary electrostatic field configuration. A small test charge is placed at a null point. It implies where E equal to 0 of the configuration, so that the equilibrium of the test charge is necessarily unstable. B. Verify this result for the simple configuration of two charges of the same magnitude and sign placed a certain distance apart. Now see, this can be proved by contradiction. આપણે પહેલા ઊંધું વિચારવાનું. આપણને અહીંયા એવું કહ્યું છે કે equilibrium is necessarily unstable. એવું બતાવો. Let's consider equilibrium is stable. તો stable equilibrium નો meaning શું થાય પહેલા તો કે if at E equal to 0 any charge is placed, and then from that particular position if charge is displaced, then the restoring force act on it towards the equilibrium. એટલે એને સ્ટેબલ પોઝિશન માંથી તમે કોઈ પણ જગ્યાએ આમ કોઈ ડાયરેક્શનમાં ખસેડો તો રિસ્ટોરિંગ ફોર્સ પાછો એ જ ડાયરેક્શનમાં લાગવો જોઈએ. હવે ઇલેક્ટ્રિક ફિલ્ડ અહીંયા આપણે 0 લઈ લીધું છે, રાઈટ? નલ પોઈન્ટ છે. અને if in any direction you displace the charge but the force on it, that is towards the null point, it implies that all the field lines are entering to that particular point. અને તો જ કોઈ પણ ચાર્જ q ઉપર ઇલેક્ટ્રિક ફિલ્ડ E માં ફોર્સ લાગે q into E in the direction of field. તો જ આ પોસિબલ થાય. હવે બધી જ ફિલ્ડ લાઇન્સ જો નલ પોઈન્ટની અંદર એન્ટર થતી હોય તો if we consider the Gaussian surface enclosing that particular null point, then charge enclosed by the Gaussian surface is 0. તો electric field 0 થવું જોઈએ. તો electric field 0 છે તો ફ્લક્સ બી 0 થવું જોઈએ. તો ફ્લક્સ 0 થયું. પણ હવે લોજિકલી તમે જોવા જાઓ તો બધી જ ફિલ્ડ લાઇન્સ જો સરફેસની અંદર એન્ટર થતી હોય તો ફ્લક્સ 0 કેવી રીતના બને? ફ્લક્સ 0 ક્યારે બને કે નંબર ઓફ ફિલ્ડ લાઇન્સ એન્ટરિંગ ધ સરફેસ અને લિવિંગ ધ સરફેસ સેમ હોય તો થાય નહીં કોઈ દિવસ. એટલે કોન્ટ્રાડિક્શન થયું. મતલબ કે આપણું જે સપોઝિશન હતું કે ઇક્વિલિબ્રિયમ ઇઝ સ્ટેબલ, નોટ પોસિબલ. બરોબર છે? તો પછી ઇક્વિલિબ્રિયમ ઓફ ધ ટેસ્ટ ચાર્જ ઇઝ નેસેસરીલી અનસ્ટેબલ. આવી રીતે કોન્ટ્રાડિક્શનથી પ્રૂવ કરવું પડે. હવે જો બી માં શું કહ્યું છે કે વેરીફાઈ ધીસ રિઝલ્ટ ફોર ધ સિમ્પલ કન્ફિગ્યુરેશન ઓફ ટુ ચાર્જીસ ઓફ ધ સેમ મેગ્નિટ્યુડ. હવે જો આ પ્લસ ક્યુ ચાર્જ તો સેન્ટરમાં ઇલેક્ટ્રિક ફિલ્ડ 0 થઈ જશે. હવે જો તમે આ સેન્ટરમાં કોઈ બીજો ચાર્જ મૂકો અને એ ચાર્જને જો આપણે અહીંથી ડિસ્પ્લેસ કરીએ તો પછી એને રિલીઝ કરી દો તો જો આ સ્ટેબલ ઇક્વિલિબ્રિયમ માં હોય તો રિસ્ટોરિંગ ફોર્સ આની ઉપર લાગે ને એ આને પાછો આ પોઈન્ટે લઈ જવાનો ટ્રાય કરે. પણ હવે પોસિબલ જ નથી. જો આ પ્લસ ક્યુ ના લીધે આ ડાયરેક્શનમાં અને આ પ્લસ ક્યુ ના લીધે આ ડાયરેક્શનમાં ફોર્સ લાગે તો નેટ ફોર્સ અહીંયા ક્યાંક વર્ટિકલી અપવર્ડ લાગશે. રિસ્ટોરિંગ ફોર્સ લાગશે જ નહીં આની ઉપર. ક્લિયર? સો વી કેન સે ધીસ વન ઇઝ નેસેસરીલી unstable equilibrium. Clear to all of you? Now 1.33. A particle of mass m and charge minus q enters the region between the two charged plates initially, moving along x-axis with speed vx. The length of the plate is L and an uniform electric field E is maintained between the plates, so that the vertical deflection of the particle at the far edge of the plate is QEL square upon 2mvx square. Now see the figure. Upper plate is positively charged, the lower one is negatively charged. electric field that is from positive to negative, means vertically downward. And now charge minus q enter to this field with initial velocity vx in x direction. So here the force on this particular charge in electric field, that will be q into E and F equal to ma. So we can write F equal to ma, that is equal to q into E. So acceleration of this charge particle when it enter to the electric field, that will be q E by m. But see, q, E and m all are constants. Clear? So we can say acceleration is constant. But now this particular force that is in the opposite direction of electric field, because this is negative charge. So under the effect of it, this charge will move in upward direction. So here, suppose when it come out from the edge of the upper plate, at that time its displacement in vertically upward direction, that is y. So vertical deflection is y. Now vertical motion, that is with constant acceleration. Horizontal, that will be with constant velocity, because in horizontal direction there is no force. So here we can use the equation d equal to v0t plus half at square. Now when it entered to the field, at that time its initial velocity is in x direction. So its vertical component, that is 0. So velocity in vertical direction, that is 0. So v0 is taken 0. And the vertical deflection is represented by y. So we can write d equal to y. This one 0 plus half acceleration, that is qe by m into t square. So resultantly we will get y, that is equal to half qe upon m into t square. Now we have to find this time t. So here the time interval in which it cover this particular distance L with horizontal constant velocity Vx. In the same time interval, there is the vertical deflection equal to y. Now, horizontal constant velocity Vx, that is distance upon time. So time, that is L by Vx. Now substitute the value of time t. Here L by Vx, so we can write L square upon Vx square. So resultantly the vertical deflection is QE L square upon 2m Vx square, and which one is this one? We want to prove it. And it prove. Clear to all of you? Now 1.34. Suppose that the particle in exercise in 1.33 is an electron projected with velocity 2 into 10 raised to minus, 2 into 10 raised to plus 6. If E between the plates separated by 0.5 centimeter is 9.1 into 10 raised to 2 Newton per Coulomb, where will the electron strike the upper plate? Take charge of electron 1.6 into 10 raised to minus 19 Coulomb and mass of electron, that is 9.1 into 10 raised to minus 31 kilogram. So use the equation derived in the previous example for vertical deflection. Y, that is equal to Q E L square upon 2m Vx square. Okay. Now here Vx, that is 2 into 10 raised to 6 meter per second. E, that is 9.1 into 10 raised to 2 Newton per Coulomb. Charge of electron and mass of electron, that is given to you. Okay. Now see here, electron is projected between the plates, and plates are separated by 0.5 centimeter. So when it is projected between the plates, it implies that plates are at a distance 0.25 centimeter from the electron. So when it strikes the upper plate, the vertical deflection, that is 0.25 centimeter. So here indirectly y is given to you 0.25 into 10 raised to minus 2 meter. Now we can use this equation y equal to QE L square upon 2m Vx square. So we want to find where will the electron strike. It implies that how much horizontal distance covered by electron, that we want to find. So we have to calculate L. So make L square as a subject. So 2ym Vx square upon EE. So L, that is equal to under root 2ym Vx square upon EE. Now substitute. Here y, that is 0.25 into 10 raised to minus 2, mass of electron 9.1 into 10 raised to minus 31. Then velocity with which electron enter, that is 2 into 10 raised to 6 meter per second. Charge of electron 1.6 into 10 raised to minus 19, and electric field, that is 9.1 into 10 raised to 2. Then solve it and then take square root of it. You will get the answer. Clear to all of you? So chapter 1 is completed.